Welcome back to the second video for TEC 259 on Monday, February 22nd. In this video, we're going to put together a lot of the topics that we've been talking about for the past 2 weeks, and we'll talk about the much more realistic situation of multiple modes of heat transfer happening at the same time. In the real world, usually you've got more than one thing going on at the same time. For example, right now, I'm sitting in my office. And think about the heat transfer that is occurring from me right now, because I'm the warmest thing. Actually, that's not true. I got a coffee maker over there. But think about my body temperature, right? And I'm kind of cold right now, as you can see. I've got the fleece on, and that's because there's multiple modes of heat transfer that's taking my body heat away from me right now. We've got convection due to ventilation in the room, maybe also some natural convection as the air around my body is getting warmed up and more buoyant and then flowing. So we've definitely got some convection. We've also got radiation. There's also radiation from my body to the surrounding the walls in the room. So I am radiating heat to the walls of the room. So I'm losing body heat right now, both via convection as well as radiation. And I guess if you want to be technical, there's probably conduction, through the different layers of clothing that I have on as well. So there's definitely multiple things going on at the same time. One thing that's kind of interesting, I mentioned that there is radiation heat transfer going on between me and the walls of the room. And that's always going to be true as long as the walls of the room are at a lower temperature than my body temperature is. And this actually explains an interesting phenomenon, and that is that you could be sitting in your living room in the winter time, and the air around you could be the exact same temperature as the temperature in your living room in the summertime, but you'll feel colder in the wintertime, right? I don't know if you've ever noticed that, but I've definitely noticed that. We don't normally keep our air in our house at the same temperature in the winter and the summer, but even if you kept your room temperature at a consistent 75 degrees year round, you could be sitting in your living room in the wintertime with the air at 75 degrees, and you'd feel colder than if you were sitting in your living room in the summertime and the air was at 75 degrees. And the reason for that is because of radiation heat transfer to the walls and the windows of your living room that are at a colder temperature in the wintertime. They're at a colder temperature in wintertime because there's heat transfer from inside to outside, so the walls are colder because they're right next to the outdoor environment. So your window, you feel your window. Your window is cold in the wintertime. You feel your walls, your exterior walls of your house, they feel colder in the wintertime. So there's actually radiation heat transfer happening from your body to the walls and windows and everything that's around you. And so you're actually losing heat that way. And there's more of that radiation heat transfer happening in the wintertime because everything around you is colder in the wintertime, even if the air itself in your living room is the same temperature in summer and winter. All right, so that's kind of an interesting thing to think about. That's why you can sit in your living room in the winter and feel colder, even if the air around you is the same temperature as it would be in the summertime. So just kind of some food for thought there. So what we'll do to start out with is a little review of the modes of heat transfer, and then we'll talk about how we can combine thermal resistances to form a complete thermal resistance network and solve problems that are a little bit more complicated than what we've been talking about so far, because they'll be more realistic by involving multiple modes of heat transfer. So with that, I'm going to share my slides because I have a little review of this. All right, combined modes of heat transfer. So we're going to start by doing a little bit of a review, and we'll talk about what modes of heat transfer are relevant for different types of material. We'll talk about solids and liquids and gases, and then also the special case of a vacuum as well. So for solids, what modes of heat transfer could you have for solids? Well, take them one by one. Let's think about them one by one. Can you have conduction through solids? Yes, absolutely. You can have conduction through solids. You can have conduction to solids. So yes, absolutely. Convection, Well, you can't have heat transfer, you can't have convection heat transfer through a solid, but you can have convection heat transfer to the surface of a solid, right? If there is a moving fluid, liquid or gas, that is right next to the solid. So, not internal to the solid, you can't have convection, but you can have convection at the surface of the solid if you've got a moving fluid, right? How about radiation? All right, so radiation is, as usual, a little bit more complicated. So it kind of depends on the solid. Specifically, it depends on whether it's an opaque solid or if it's kind of a clear, clear or translucent solid. So if you've got an opaque solid, if I've got just something like this, then I can have radiation heat transfer to the surface of the solid, but I'm not going to get radiation heat transfer through the solid because it's an opaque. So it doesn't allow radiation heat transfer to pass through it. But think about something like windows. If you're standing inside a window, you definitely get radiation heat transfer and energy transfer in general through a window, right? That's what light is. Light is radiation energy, mostly in the visible spectrum, but it's coming through the window. So you definitely do get, or you can get, radiation heat transfer through a clear or translucent or transparent solids. Different solids interact with radiation in different ways, and this is largely the effort of modern window manufacturers is to try to only let the desired wavelengths through. You can design materials such that they absorb different wavelengths of energy at different rates. So you might design a window to try to absorb the UV light while passing most of the visible light through. So this is really important. This study of how radiation heat transfer interacts with solids, especially glass, is really important to the modern window industry. So in general, what I want you to know, radiation heat transfer can transfer to the surface of an opaque solid. And in general, it can pass through a transparent or translucent solid. All right, how about liquids? Can you get conduction through a liquid? Well, only if the liquid is still and not moving, right? Because if it's moving, then that's not conduction, that's convection. So can you get convection heat transfer through a liquid? Yes, definitely, but only if it's moving, if the liquid is moving. All right, now radiation, as we mentioned before, it's a little bit more complicated. So once again, it kind of depends on the liquid. If the liquid is opaque, imagine like an opaque liquid, then it behaves kind of like an opaque solid. And you get radiation heat transfer to the surface or very close to the surface, but it doesn't penetrate very deeply, if at all. All right. But then again, if you got a transparent liquid, like say I don't have a clear glass on my desk right now, but say you had a clear glass of water, right? Well, if you had a clear glass of water, then the light can pass right through. And if the light in the visible wavelengths can pass through, that's a pretty good indication that the infrared wavelengths, which are heat, can also pass through. So that's in general true, that transparent liquids allow radiation heat transfer to pass through them, whereas opaque liquids can have radiation heat transfer to the surface of the liquid, but generally not passing through the liquid. The exception, and it mentions it here, is when you have lots and lots and lots of liquid, like say a big lake or a big ocean, because even though water, even lake water and ocean water, even though that's pretty much transparent or at least translucent, you've got so much of it. There's just so much water in a big lake or in the ocean that below a certain depth, all of that radiation energy is absorbed. And this is why if you go deep enough in the water, there's no light. I don't know off the top of my head. I don't know. I don't remember if that's 100 feet or 200 feet or more than that. But certainly, the deeper in the ocean you go, the less light there is, and you don't have to go anywhere near the bottom of the ocean to find that all the light has been absorbed and the radiation cannot pass through. So that's kind of an exception. If you have a really large body of water or a really large liquid, even if that liquid is transparent or translucent, then there comes a point when the liquid can absorb all of that radiation and there's no more to pass through it. All right. So liquids do interact with radiation, but it just kind of depends on whether it's opaque and translucent and how much of it there is. All right. So radiation is one of those things that's a little more complicated than the other two. So it depends. And then we have gases. Can we have conduction through a gas? Yes, like liquids, but only if it's still. Can we have convection with gases? Yes, like liquids, but only for moving gases. Do we have radiation heat transfer with gases? Generally not. It's a stretch to say zero. You know, it's hard to say there's zero interaction with gases, but usually very little. There's very little radiation heat transfer to the gas. In other words, it passes through. All right. So in general, radiation heat transfer will pass through gases and will not interact with the gas or transfer the heat to the gas very much. It's not to say none, but not very much. And a good example, like it says here, ozone in the atmosphere or at the top of the atmosphere does a pretty good job of absorbing UV radiation. That's radiation. That's energy transfer. But most of the radiation heat transfer passes through the gas in our atmosphere. And our atmosphere doesn't interact a lot with the radiation energy transfer that's passing through it. Vacuum, like in space, that's the last thing that we can talk about. That's easy. Is there conduction through a vacuum? No, because there are essentially no molecules, and conduction heat transfer needs adjacent molecules. Is there convection in a vacuum? No, because once again, there's no molecules, and convection relies on the molecules moving around to transfer their thermal energy. So there's no conduction and there's no convection in a vacuum, but there is radiation, because that is just electromagnetic waves that don't need any medium to pass through. So as we saw before in the previous slide or two, radiation can pass through certain types of solids and liquids and gases, but it doesn't need a medium. It doesn't need a material to pass through. It can travel through space perfectly fine. All right, that was the review of different modes of heat transfer. And the equations on this slide and the next slide are not new. You've seen all of these before. It's just a review of the equations that we have used. All right, so we started out with conduction, and we started out with Fourier's law of heat conduction, but we said, you know what, that's not really in a very convenient form for us to use for all but the very simplest conduction equations. So we did a little bit more work that day when we talked about conduction and put it in a more useful form, which was this. So we did a little extra work that day, and today is the day where that pays dividends. All right, because we did some extra work that day, but now we can say that this is going to work really nicely for us because all of our equations for heat transfer, conduction and convection and radiation, they're all in a similar form, kind of like this. And because they're in a similar form, we can combine them very easily, simply by combining resistances. So that's really all we're going to do today, is we're going to combine thermal resistances for conduction with thermal resistances for convection and potentially thermal resistances for radiation. And those resistances can be combined, depending on the situation, in series or in parallel. So does the heat have to go through the conduction part first before it can be convected? If so, they're in series. Can the heat transfer via convection or via radiation? Does it have a choice? If so, then they're in parallel. So think about it kind of like that. If the heat has to transfer through one mode of heat transfer and then another, then that's in series. If it has a choice whether to transfer via one mode or another mode, then that's in parallel. And we will add resistances in series and in parallel, just like you do in the electrical domain for electrical resistances. All right, so that's basically the gist of today. That's really what there is today. So this was the form of the conduction equation that we like to work with, that is most convenient. And the only thing you really have to recognize here in conduction is, what is that? Well, thermal resistance for conduction is L over Ka for a planar surface, like a wall or something. Or if you've got a pipe or a cylinder, then you need to use this equation for the thermal resistance for conduction for a cylinder or a pipe. All right, so we used those a couple of days, a week ago or so. So you got to calculate these. Once again, you can have conduction in series or in parallel. So you can combine these in series or in parallel. But once you do, you get the thermal resistance for conduction, and you plug that into this equation, and out pops your heat transfer, your rate of heat transfer, Q dot. All right. Then the next time we talked about convection heat transfer. Convection's a little bit more challenging than conduction. And the big challenge with convection is finding H, the convection heat transfer coefficient. So we talked about the different non-dimensional numbers, the Prandtl number and the Nusselt number and the Reynolds number, not in that order. Usually you go Prandtl number, Reynolds number, Nusselt number, but you got to use those non-dimensional numbers to find H, the convection heat transfer coefficient for that situation. But once you got that, once you got H, then it's pretty easy to find the convection resistance. It's just 1 divided by HA. And then once you got that, you plug that in here to this equation, and then plug that into your calculator, and out pops Q dot, the rate of convection heat transfer. All right, so it's not too much of a stretch to say, let's say we've got a solid material and convection on one side of the solid material. Well, we've just got two resistances in series. You've got conduction through the solid material, and then you've got convection from the solid to the liquid. So those are literally just two resistances in series. So you could calculate this thermal resistance for conduction through the solid material if it was a planar wall. Otherwise, you'd use this one if it was a pipe. And then you got that resistance, and you calculate the convection resistance, and you just add these together because they're in series. If the thermal energy has to transfer through the solid surface via conduction and then transfer through the convection heat transfer, they're just in series. So you just add that plus that. The radiation was a little bit more complicated. We had to define a couple of different resistances called surface resistances and space resistances. And we wanted to get the basic radiation equation, this, in a familiar form, where we've got Q dot equals the difference in temperature, not the difference in temperature to the fourth power or anything like that, but just delta T, the difference in temperature, divided by some R for radiation, some resistance for radiation. Because it's in this form, and this form looks exactly like this equation on the previous slide, and this equation on the previous slide, this is just a delta T. You know, it's called T sub S for the surface minus T sub infinity for the bulk fluid temperature, but this is just a delta T. This is just a temperature of one thing minus temperature of another thing. So this is really the same form right here. So because we put our radiation equation in the same form with just a delta T here, temperature of one body minus temperature of another body, we can combine this resistance with the resistances for conduction or convection in series or in parallel. So we talked about these equations last time. Here is your surface resistance for a body. Here is your space resistance from one body to another body. You combine those in series to form your surface plus space resistance. That's this term right here. And then to get R rad total, the total radiation thermal resistance, you use this equation right here. And we had to use this equation right here to plug in here because we wanted to get this equation in the same form as those previous equations for conduction and convection, where all we had was T1 minus T2, or the delta T in the numerator here. As long as you get it in the same form, then we can combine those thermal resistances, this thermal resistance with the conduction and or convection resistances. All right, so the resistances that we've got this one for radiation, and we've got this one for convection, and we've got these two for conduction, depending on whether you got a planar wall or a cylinder. So those are the equations that you're going to use for the resistances that you can either put in series or in parallel, depending on whether the heat has to go through one mode of heat transfer to get to the next, then they're in series, or if it can choose, then they're in parallel. All right, so this is kind of what I just said. So we now have these thermal resistances between the different bodies and across interfaces between different bodies and materials, and we can just add them together exactly like electrical resistances. So if they're in series, then we add them directly, R1 plus R2 plus et cetera, et cetera, et cetera. If they're in parallel, a good example of parallel is I've got something hot in the middle of the room, and I can have convection around this. You know, I have a convection happening at the same time that radiation is happening from this body to the walls. So if they're at a different temperature, then I'm going to get radiation heat transfer as well as convection heat transfer. That convection might be natural convection, or it might be forced convection due to ventilation in the room. But if you've got a good example, if you've got like a hot object in the middle of the room, then you're almost always going to have both some type of convection and some type of radiation happening simultaneously, which means they're in parallel. So if we have that situation, we can combine them in parallel by just adding them inversely. And remember, we have 1 over R total equals 1 over R1 plus 1 over R2 plus ... etc. All right. Just remember, the easiest way to mess this up that I see is to remember that this is 1 over R total. It's not just R total equals 1 over R1 plus 1 over R2. In fact, it's 1 over R total equals 1 over R1 plus 1 over R2, etc. All right. So if you want to find R total, you got to take this entire thing to the power of -1, which means it's just the inverse, which means it's 1 over this whole thing in parentheses. All right, so here's a couple of examples. We'll talk just kind of here and in the next slide about what we would have in these situations. And then I will work an example out, and we'll talk through an example with calculations, okay? But these first two, we're just gonna talk through it without doing the calculations, and then we'll move to one that we will do the calculations for. So here's the situation. What kind of heat transfer do you have? And is it in series or in parallel? Over here, we've got a moving liquid, and over here, we got a moving gas. So what does that tell you? Especially in light of the fact that this is a solid. So here, this layer is a solid, and this is a layer of insulation. So this is like a layer of like fiberglass insulation or maybe foam insulation, something like that. Either way, it's a solid. So this is a solid, and this is a solid. And over here, we have a moving liquid, and over here, we have a moving gas. So hopefully it's pretty intuitive to you that between this moving gas and this solid insulation, we have convection. So we have convection, that would be like a resistance right here. And then same thing over here, this is a solid, so we have heat transferring from or to, we don't really know, one or the other, from or to the moving liquid to or from the solid steel. So we've got convection happening over here. So there'd be a thermal resistance right here for convection. Then we got this solid steel. All we're going to have through the steel is conduction. And similarly, all we're going to have through the insulation is conduction. So what this thermal resistance network would look like, well, first of all, think about, are these in series or in parallel? So can the heat transfer from the liquid to the steel at the same time that that heat is going through the steel? No, it's got to go through one and then the other. So if that thermal energy is transferring from over here at T1 to over here at T2, it's got to go through these layer by layer. It's got to be, that heat has to be convected to the surface of the steel by the moving liquid. Then it has to go through the steel. Then it has to go through the insulation. And then it has to be convected to the bulk fluid temperature, T2. All right, so because it has to go through one, then the other, then the other, then the other, these are all in series. So if I was to draw this thermal resistance network, I would draw 4 resistances in series. The first resistance would be the convection from the moving liquid to the steel. The second thermal resistance would be the conduction through the steel. The third thermal resistance would be conduction through the insulation. And the last thermal resistance would be the convection from the solid insulation to the moving gas. So we don't know in this example which is hotter, T1 or T2, and that would determine whether we have thermal energy flowing from left to right or from right to left. Here's another example. We've got a body 1, so that's like a solid body 1, like a piece of steel or something. And we've got a gas, and we've got body 2 over here. All right, so what do we have in this situation? So we have some body, and it's at a certain temperature. And we've got body 2, and we can hypothetically say it's at a different temperature. So in that case, there would be a delta T. And if there is a delta T, then there will be heat transfer, because delta T is what drives heat transfer. So if we are going to have heat transfer, then what mode is that heat transfer going to take? Well, we've got a gas right here. So the question would be, is this gas moving or is it still? And most of the time, you're probably going to have moving gas in here. The gas in here is probably going to be moving, but it kind of depends on the parameters of the problem. It largely depends on how wide is this gap, because if the gap is fairly wide, then you can start to get some natural convection. You know, if body 1 is hotter, then the gas on this side of the gap is going to be hotter and more buoyant. So it's going to set up a circulation up, and then it'll come back down on this side and it'll sink as it gets colder. And then it'll set up a natural circulation flow like this. But if that gap, this distance right here, if it's very narrow, then there might not be enough room. Like, just, it won't set up that natural circulation flow if that gap is too small. And this too is a very important subject for windows. Measuring that gap. You might know that the vast majority of windows nowadays are double pane. So they have 2 window panes separated in the middle by a gas. And that gas might be, typically it would be argon or krypton in some of the fancier windows, but most windows are going to be double pane. There are some triple pane windows. They're not as common, but they're much better for insulation. But just think of this right now as a double pane window. This gap right here is really important to get the performance of the window at the highest possible level. If your gap here is too large, then like we just said, you're going to get a natural convection circulation here, which is going to increase the rate of heat transfer. Because convection, like I talked about earlier, convection is a faster form of heat transfer than conduction is. All right, so if this gap is too large and there's too much separation between the window panes, then you're going to get natural convection between the window panes, in the gap between the window panes. But if that gap is too small, all right, then you're not going to get natural convection. But now think about your conduction heat transfer. It's L divided by Ka. That's the resistance, right? So if L is really small, then you're reducing your thermal resistance from conduction. So there's this kind of like, there's this compromise between having the gap too small, in which case your conduction heat transfer thermal resistance will be small and you'll have greater heat transfer. But if you get that gap too large, then you set up this natural convection in here. So it's really quite a science to get the gap between the double pane windows just right to make the thermal resistance from body 1 to body 2 as much as possible, as high as possible. All right, so I've kind of said a lot about that. So we're going to have some method of heat transfer between here and here. We're also going to have radiation, and I don't think I mentioned that yet. But if there's a temperature difference between these two bodies, then we are going to have radiation heat transfer. Depending on, the exact amount depends on these bodies. But in general, we're going to have radiation heat transfer between these two objects that are only separated by this layer of gas. So what are we going to have here? Well, it depends on the problem, and I'd have to give you more information. But you're probably going to have either radiation heat transfer in parallel with conduction heat transfer through the gas, if the gas is not moving. Or if this gap is large enough, then you would have radiation heat transfer from here to here in parallel with probably a natural convection for the molecules of this gas as they're flowing around. So my best guess here is you're probably going to have either a combination of radiation and conduction in parallel, or you're going to have a combination of radiation and convection in parallel. All right, so you'll have to calculate those resistances and then combine them inversely. 1 over R total equals 1 over R1, where that might be the radiation, R rad total, plus 1 over R2, where that might be the either the conduction or the convection thermal resistance. Okay, yeah, well, it depends on whether the gas is moving or stationary, like we already talked about. All right. That is the end of the slide presentation. So I think I might cut off the video here just to keep things kind of short and manageable. And in the next video, I will work through an actual calculation problem that's kind of like the homework for the next class. So I'll cut this off here, and I'll see you in the next video where we will work out a combined modes of heat transfer calculation problem. See you in the next video.